Hello, listeners. Yamina here. Welcome to the Dr. GPCR podcast. We are excited to share that the Dr. GPCR Ecosystem 2.0 platform opens to all beta testers starting June 15th, 2022. We plan on opening the ecosystem slowly to resolve any kind of kinks as soon as possible. You can visit us at ecosystem.drgpcr.com and explore the new site. Access is restricted to members of the GPCR field, and each sign-up will be approved based on one's involvement in the field. Once your sign-up is approved, you'll be able to enter the ecosystem. You'll also have the option to select a plan and get access to all things Dr. GPCR, including the upcoming Dr. GPCR Summit, access to new podcast episodes before they even get released to the general public, our new group discussion and forums, our new and improved job board, and Learning Center, where you'll be able to take a course or even prepare and share a course with your colleagues. Discover GPCR companies in one place and much more. Take advantage of everything that the new GPCR dedicated online playground has to offer today by visiting ecosystem.drgpcr.com and signing up. This is the only place where GPCR scientists, trainees, and GPCR organizations can thrive and where it's only about science and GPCRs. Think ResearchGate meets LinkedIn meets Amazon at the tip of your fingers. Visit ecosystem.drgpcr.com to start your journey today. Also, make sure that you mark your calendar for the third edition of the Dr. GPCR Summit. This year, the summit will be held between October 10th and 16th. Stay tuned for more soon. Visit ecosystem.drgpcr.com or visit our old website, which is still active, drgpcr.com, to explore everything that we've been doing in the past 2 years. And now, let's dive into this episode. Hello, everyone. This is Yamina from Dr. GPCR, and today I am delighted to have my friend and colleague, Dr. Martin Audet from the University of Sherbrooke with us. Hi, Martin.
Hi, Amina. How are you doing?
I'm great. I'm so glad we finally get to do this.
Yeah, it's been a ride. It's been a ride, but
it's been 2 years.
We made it. We made it.
Exactly. So, it's Friday night. I'm excited to talk to you. You have your coffee. I have my special drink in my mug. So let's start at the beginning. Oh, it's beer, basically.
Yeah.
Because I needed something. It's Friday. Here is my first question. Why don't you introduce yourself briefly and talk to us about your story as a scientist?
Yeah, so as you say, my name is Martin Audet, and I'm an assistant professor at the University of Sherbrooke at the Faculty of Medicine. So I have a research group with 2 students, a postdoc and a research assistant, and a few interns, and we are doing structural biology, and our interest is how the drugs act on the G Protein-Coupled Receptors, on also how they are transported through the membrane. So we're studying also SLC transported. So basically all membrane protein. And so my background, actually, I did a Ph.D. in biochemistry with Dr. Michel Bouvier, which is a professor at University of Montreal. So I think a lot of people know Michel, and so was a great mentor for me. Really appreciate my years with Michel. Really, I was in a great gang there with students at that time that studied with him, and we were still like we're very good friend, and actually, we know each other from probably that time and maybe before, during even undergrad. So so I did this page in biochemistry. Michel was and he's still a very great pharmacologist. So basically, my strong background is really in pharmacology. Although I was really interested in the theoretical background pharmacology and more on the biophysical approach we can develop for GPCRs to look at signaling and more going beyond than just measuring signaling among like the signal from each families, but really going deep into how can we really monitor like each G protein actually. And so that was the beginning of the story. And it's been like there are a lot of people that worked on these and it did like fantastic like tools to study signaling. And then I move on and I went really deep in structural biology. I did my fellow at Ray Stevens' lab at first at the Scripps Research Institute in San Diego, and then we moved to USC in Los Angeles at the Michelson Center and the Bridge Institute, actually in Michelson Center, and that was great, great years too. Really thriving these years in Los Angeles, and actually, where I was with my wife and my entire family, and it was great. Actually, Ray was also one of the great mentors I had. Actually, I got two great mentors, and really teach me a lot about these. Also about it was about like structural biology of GPCRs and how to really go deep in the biophysical aspect of this. And we're a fantastic group. Actually, we're great. We did a lot of nature and paper, a lot of high impact application cells, and that was great time. Actually, that was really fun. And I miss these time where everything was easy because we had these mentors that were making life easy for us and taking all the thunder, all the storm for us without even telling us that what's going on. But it was really great time, and I know I say it again, but it's we did a lot of discovery, and so now I started my own group in 2019. So just before the pandemic, and so it was so starting my group at University of Sherbrooke was not difficult, but there were some challenges because I was the only protein crystallographer there, so there were no really infrastructure at the beginning for this. Now we're well equipped. That's great, but. And especially like 6 months after I started, there were the huge pandemic that were starting, and then I remember I had like my first student, Eric Barbeau, and we just received I think it was in February and 2020, and we had these boxes with the centrifuges and the pipette box, pipette tips, everything new. Like we just ordered, we received it, and we kind of unwrapped everything, look at if everything is there, plug the centrifuges, and then 3 days after we heard that the research center just closed for like 4 months. Yep. So that was really crazy time. And then after, you ask yourself, I'm starting my group, and how can I survive? And I think we all did that. I mean, for all our reason, and we all got into like I remember like I was opening a blank Word file and just writing down the ideas that will allow me to survive in science, because you can't at the beginning, pass too much time outside productivity. It's really critical, and you're the only one that can do that. You have nobody really to put the hands in the wet lab. So that was crazy time. But I just planned the stuff. I think I was pretty successful.
Well, you had time to plan.
But it's all about planning, and I cannot thank too much Ray for showing me like how to get organized correctly and get these Gantt charts rolling and everything about management. And I think that's kind of saved the day. I was now we're well equipped. Everything's going. We got our first paper that accepted, and
Congratulations.
Actually, we just received the proof today, so I need to. After the recording, I'm going to work on this.
That's awesome. Yeah, it's the right time.
I'm going to correct the thesis of the other.
Yeah. It's the right time. Okay, so you mentioned in the beginning that you were in Michel's lab, and it's so funny because I kind of know your story. So I'm sitting here saying, well, yes, I know this, but let's take a step back and make a full disclosure. So you and I have known each other for 22 years, which is even horrible to say, but we did start undergrad together.
We're the children of human genome sequencing publication in 2000. We enter our science program, biochemistry program in times where it was a big revolution.
Yes, exactly.
Revolution. That was amazing. Okay, how can you not love science after that?
Agreed. But let me take you a step back, because I don't think I've ever asked you these questions before. As a child, as a teenager, did you always know that you wanted to be a scientist?
That's a really good question. I think at the beginning, yes, but I did like college in music.
Actually. I know that's what I was getting at.
So I was strong in music. I was strongly involved in music. I played violin until 12 years old. I was listening only classical music. I was this type of kid. A little bit like good at school, a little bit isolated, and playing violin and striving on symphonic orchestra, and then at 12 years old I became a teenager, and then I had friends, very old friends that he had long hairs and was listening to rock music, and then I decided to play guitar.
I knew the guitar. I did not know the violin.
Yeah. And then in order to buy my first guitar, then my mom kind of sold my violin at that time. I bought it back, by the way. When I like 10 years after, when I as a grad student, I bought it back, but the same one, but not the same one, but the same model. And then I bought my first guitar at 12 years old, and then I played, and then I was we were doing like shows during high school every month, and then I tried. I got auditioned at college. We call in Quebec Cégep, but it's it's post high school, and it's just before university, but post high school we got a 2 years, and then I entered in the music program, and learned like quite interesting things about music and the theory. And then I entered in music actually at the University of Montreal. That's how I started my university. It was in 1999. And then I switched to biochemistry, and then I meet you.
But what happened?
Well, then I found so. The story short is that so science is very strong in my family. My dad was a chemist, he studied chemistry, and then he worked not directly as a chemist, but at the beginning, yes, but then. He switched to kind of management stuff, but he was at Johnson & Johnson, so the pharma company. It's not there anymore, but it was in Montreal. Now it's I can't remember what it is now, but so my brother actually has a degree in biology, and then he did the grad study in the AudetLab. Actually did his PhD in pharmacology. So, and it's funny because he published his first paper as a first author with Michel before I did publish, and we were doing our PhD at the same time. Wow. So it's really confusing because his name is Nicolas, and so it's M Audet, and me it's M Audet. So people still confuse us in scientific meeting else, and That is funny, and we're basically look alike.
Yeah, I know Nicolas as well. So yeah,
Yeah,
I know that I can make the difference between the two of you. I think because I've seen you first, and I met Nicolas afterwards. But yes.
Yeah, I'm surprised. Everybody's surprised when they look at your face and they say, Nicolas? Oh, who are you? You're Nicolas,
which one of you?
But a bit different. And it happens actually at the last Great Lakes retreat. There were people from McGill. But then my brother is now he's the director of the microscopy platform at McIntyre Tower. Actually, so in the pharmacology and therapeutics department, and at McGill, and so the student there were some students from the pharmacology department, and it actually happened. It was in the parking lot. And say, oh, are you the brother of Nicolas? So we basically have the similar face, probably.
Was it this meeting or in 2019?
No, it was this, but both actually. Both, but I remember clearly this meeting like a week ago because and so it's always been really funny. But we have these Christmas moment where we start talking about science and become really, really deep. so actually, it's probably there's deep roots in my family about science, and one was a chemist, the other a biologist at the beginning. So I thought probably biochemistry was the real deal.
Good match.
So that's probably what made me decide it. And I remember, what really, really happened. I just truly, it's a true story. There's the streets in front of the old main building of University of Montreal, and it's really high on a mountain. So you're down. I think it's Edouard Montpetit Street. And then you have to look really up, and because it's really high. It's on the mountain, and then you see the big old building, and I remember really. Actually, I was at the music school of University of Montreal at that time when that happened. And the music school is at Pavillon Claude Champagne, so it's really on the other side. But you need to pass in front of the main building where there's the science. The sciences and the chemistry, biochemistry, and biology, and so I passed in front of the building, starting my music degree, and then I got it was like a love at first sight, and I was just I'm a good musician, but I want to be there. It was really, I don't know what happened. It was really. It was early passions. I mean, love for science that just struck me greatly. And I think I was doing good at science before also, but then I really realized that, this is some things I need to explore just in my mind, trying to, pick up my brain about nature, the fundamental of nature. That's the question. How does it work? What is the right model? How can we understand the basic of nature, and that was really, really deep, and it's still very intense. I cannot stop talking about this. And
that's such an interesting story. I knew that you were in music before, and then you switched programs, but I didn't realize that it was just walking in front of the main building, and it's an impressive building, and so it's Roger Gaudry, and what I liked always about that building is the fact that in the tower there's the library, and if you are in the library, you can actually see Montreal really nicely. I can see you laughing. So what's the story behind the tower?
So it's a special library actually, and it's really. It's really a tower, actually.
It is. It's an interesting.
Really high, and the thing is that it's amazing, actually, because when the thing is that you don't realize they really kept their like really deep stuff. So I was an undergrad, so I was always there, and because one of the things that I love a lot is historical facts about science, or maybe trying to understand the socio-historical context of science. Because I always think that, that if we can understand that, we can understand how we can push science forward also.
Yeah, agreed.
Because there's always a discovery come in the context of the social context and economical context, and in the within the personality of the scientists and the group of scientists that does it. And
this is the social context here.
So the social context. So when you enter, you're gonna find this in the library, in the library actually. So what contained this tower? It contains like all the editions of Nature, for example. Like I think it started in the 1850-ish. Yeah. And this was, really interesting, because when you read that, you realize it's a response. It's a response of what? So private editing. It's a response of, you got, before you had the Academy of Science. So it was the only way to publish something.
Yeah.
And what happened is that at that time, what happened? You had to have your manuscript, and then you had to defend your manuscript in front of a, Royal Academy of Science, Académie des Sciences in France, or and you had to, and it could take years. Yeah. You could have to come back, defend. And one of the great example is the evolution theory. That the book, and you can go to the Royal Academy of Science in London, and you're gonna have have picture. I don't think you have the right to take picture of that, but I do have. I should not say that, but and then you have the room.
You have a mental picture.
Yeah, exactly. It's a mental picture, but you have the room where the Darwin kind of defend his book and try to have the things like discuss about this book with the Academy. And so it was becoming like overwhelming, and it's at a time where so before the science were financed by royal people or rich people that were kind of and it was the moving of science towards public funding actually. And so there were more and more scientists. There were public funding for emerging public university or university at that time, and there were a lot more scientists, young scientists. They couldn't publish because there were no, if you were young, couldn't have like this interview at the Academy of Science, and then and you got the private publisher that came, and that it's here for it's 170 years ago, and Nature was one of the first, and it's still there today, and that's so you have to go back and open these old Nature edition, realize all these stuff when they first analyzed milk, these
exactly
things, all the things we're taking for granted, and you got these it made a Nature, or perhaps a lot of these discovery that we are taking for granted. So it's also, when you enter in a library, you really step over the shoulder of your predecessor, and you read your predecessor, and when you read the text of your predecessor, these people are, they're not living anymore. It's like more than 100 years old, and even like some things like 30 years old. Like these people, they don't live anymore. Or they're not. If they're alive, they're not
working anymore.
Really there. And but towards like what you left, it's writing. It's the writing, and that's through the writing you can sense what was the mind of the people that were before. You read like old structural biology paper from the 60s, at the time that they were like trying to crystallize hemoglobin and stuff like this, and they got these very low resolution model made of clay, and they were drawing like they had this. Yeah, they were drawing like the electronic density, but layer by layer. Yep. So each layer was drawn by a postdoc, and then you got this calculation that how many postdoc hour would you need to solve a structure? That was crazy. Wow. Like this. But you need to know these stuff because things were very hard before. Also, we think that it was hard now. That everything is harder. It's not true. Things were really hard.
Yeah.
People. So what is the common things? It's really you really need to put your idea together, and money matters, but doesn't matters that much actually. Look at Francis Crick model. It's made of beaker clamps, and yep. It's made of ventilation duct. Actually, they cut the base of the DNA like model to the ventilation duct, and they draw the orbital on it.
Wow!
So you can see the reconstruction of the model in the Science Museum in London, and it's a lesson. These guys they took, because you couldn't build really a model at that time out of a standardized software, or you need to build it with the material that you have, and in your lab, and it was ventilation duct. It was
hey, whatever works.
Beaker for chemistry, and so it's a lesson for all of us. And I think I had that in mind when I started my group and the pandemic just started. I know that if I had the right reflection, the right idea, I could write good grants anyway, and focus on getting the right data, and I could really have my grants, and I got my grants, so everything like kind of settled. But it this is like I'm kind of swimming in the spirits of science. I don't know if that's sort of crazy.
No, it's not. I can tell that's you.
I love going to the synchrotron, for example. Why? Because there obviously I can collect diffraction data, but because there's a lot of synchrotron. You get like you get at APS, like in Chicago, you got 3 lines for for biology, for biomolecular detection of diffraction. But the rest, you got stations lines that of more dedicated to physics now, studying really the fundamental of universe, basically the material and everything. And it's always it's fascinating. These guys they know how to really they navigate in really deep like hypothesis, and it's you're in the middle of like a brain field. Basically.
Yeah,
of you go to the cafeteria, you don't know you're gonna meet a Nobel Prize or somebody very special. Yeah,
amazing.
So I love going there, and everything that is really linked. One of the biggest threat of the pandemic, and I know it was dangerous. Like COVID is dangerous. It kills a lot of people, but I think in term in a less concern matter, but it's still concerning. I think the fact that we couldn't meet scientists together.
Yeah.
In face to face, not through like electronic meetings, but really discuss about science by feeling the reaction in front of a crowd of the other scientists. That it could, a real face cannot lie, and you can really sense the input. When they don't want to tell you something, on your hypothesis that may be wrong.
Like, my camera isn't working.
or you really have something, and you can transmit, and you can communicate. I think that hurts a lot. That the fact that we couldn't get together, and I think science is it's about like hypothesis, it's about like proof and brain, but it's really about emotions. And the first things about an hypothesis, you get very intuitive. It means that your emotion is going rogue. Like you get excited.
Oh yeah, absolutely.
And then after you found why, but it's a mixture of it. So
exactly,
so, and this you can only develop this. I think person. For me, actually, in person. I mean, you want I never met like people. Unfortunately, type of people like Richard Feynman. I don't know, not the physicist. He won the Nobel Prize. He was an amazing professor, and I watch a lot of YouTubes of his classes, and it was amazing. Like, imagine a guy like this. You were stuck with you couldn't have him like in person. Well, our generation we can only have him like on YouTube, but it's so you have these guys that are really pushing our science and helping us to push our science, and Michel Bouvier, Bob Lefkowitz, Brian Kabilka, Ray Stevens, I'll say Brian Roth. These people, they are really bright guys that are lifting the young and pushing us in the right direction. So it's a long term, but this tower at University of Montreal, it was impactful. Like first seeing it, switching to science, and then entering these towers, getting very upstairs and very high, and looking and finding like these old manuscripts. Reading in the mind of their predecessor. Because you need to read in the mind of your predecessor to get on their shoulder, and then you can do some science, and it's really important. I have profound respect for older scientists and my mentor. It's so important.
It is, and I remember the library. We spent a lot of time studying in the library. I took naps in the library between exams. A lot of things happen in that library, And we studied. We were told to not talk so loud. But one of the nicest places in the library was really the backside of it, where you did have these collections of old dusty books, the smell was already just amazing.
You got these things like the first a copy of the first procedure to do a radioligand binding assay in the 70s by Bob Lefkowitz, and it's all these things that are amazing for things that we're doing in our lab now. We're taking from granted. These guys were genius to think about. Obviously they were in need, but you have to do it, and you have to try to understand what you're doing. Now we've been trained to understand it, and we can speculate out of it. Imagine you're the guys that are doing it the first time. That's not easy. For example, you got when André Deléan, they threw the guanine nucleotide on membrane, realized that you lose the high affinity of your agonist. What could going on? What's going on? You need to model it mathematically and try to understand. We are taking from now we know it's a G protein. Actually, it was calling at first it was the G factor.
Yes.
Because it was just in the presence of guanine nucleotide, and then they realized it was a protein, and then they named it G protein. That's how. I
know that paper. I know that paper. I cited it a couple of times.
It was, if you read these, I mean, what? We are in the era of big data. We have access to tons of data.
Yep.
And we're trying to modelize these data. We're trying to understand tons of data. Are we successful? Imagine these guys, our predecessor, the guys that they took a really, really tiny amount of data, and they were able to extrapolate all the modern pharmacological theory with it. It's amazing. Think about it. Think about it. They couldn't clone like 300 GPCRs and try to see if everything. Well, it's a good idea maybe to try it, but and see which one if you have the ligand, we should try to every. Well, never mind. But they had this tiny amount of data, and they were able to really extrapolate accurate theory about pharmacology. So these guys were that's what I call like genius. It means that they were building they were extrapolating their hypothesis through a huge theory, and it was accurate. They had the correct the correct intuition, and the more data we had after, then we realized that they were by signaling and synthetic ligand. They got these special properties. They were not stabilizing the same conformations, probably for some of it, than a natural ligand. And then we were more sophisticated after, but we had the data to see it. So before they had to work it out. They had to think about it, and they had to. It's like creation, actually.
Yes, but think about it. We're at a point where yes, we can generate so much more data, and then we need a way to process it and to get to that point. And but I want to take you back a little bit, because I think you made a great point as to the fact how difficult it was to even run a binding assay or to clone. Just to run a PCR when you would do it by hand and take the tube and put it in different temperatures.
I mean, I remember I'm the last generation that actually sequenced a gene. It was in 2001. I was at an undergrad at McGill University. I was studying at University of Montreal, but I was doing an internship at the Vincent Gigard laboratory. The guys who cloned the ER alpha, actually, the estrogen receptor, and I'm the last generation who actually sequenced the genes with the Sanger method, using like your sample, and you just throw it through different baths, at different temperature, and not using a PCR. And then, at the end of the summer, they bought like a PCR, and they had these PCR sequencing after.
Wow!
But it was it was with S35 when you get like a meter long for 1 or 2
and then you had to read it,
and you get like a 1/4 millimeter thick gel of polyacrylamide, and at the end of it, I had to read the gel, and at the end of the summer I couldn't feel any of the finger of my or any of the tips of my finger. It was because polyacrylamide is zero toxic, but then it's just the skin and then one back. Correct, I'm okay now, but
that's good. See, I did not know that you spent your summer in 2001 in Vincent Gigard's lab.
Yeah, actually, it was a really great experience, actually, and there were great people. It was in the MOG, so the molecular oncology group. I think it probably still exists, and it's fun. It's like 21 years ago, and so the young investigator at that time, they're probably really senior right now, but
so here, hold on, let's take a step back, because you said 2001. I thought the summer of 2001 you were doing your like mandatory internship in Michel's lab. Was it 2002?
2002, yeah.
Okay, so I'm completely lost with my dates here. Okay, I was just that.
Yeah, actually, I remember it's 2001 because that's how I met my wife.
Oh, okay. I thought you met her at the University of Montreal. Okay.
Yeah, yes, but she had an internship at McGill, actually, in 2001, because she's 1 year before me.
Yeah, I know that
because of my special things in music. I went to study music, so I was like a year or two older than the people that actually had the normal courses. But so my wife was 2 years younger than me, but she was 1 year above me. So she was doing her mandatory internship in 2001, and then she found an internship. So there were positions. So she called me but I was not with her at that time.
Mm-hmm.
But then, I got interviewed by Vincent Gigard. I got the position for the internship, and then I was with my future wife, and then we hang out, and then things happen.
And then 20 years later, there you go.
It's been all that time, and we went across the world together. And
wow. I didn't realize I had my dates all completely crossed. In my mind, the internship, the mandatory for the program was in 2000, but no, then you're right, 2001.
Yeah, 2002. Well, 2002 was mandatory because the 2001 was the first
year. Yes. Yeah, I was
so I did one. Yeah.
Okay, so we talked about the library and what it represents for you. I also loved studying at the library, and I think it was just had this very special feeling. But let's get back into GPCRs. So you kind of told us your story as to how you went from music to then biochemistry to then a PhD in biochemistry and then a postdoc. But when did you? How did you first hear about GPCRs? And when was that? I know the answer, but I'm going to ask it anyway.
Well, it's well, there were these. Obviously, we have these. We had classes about it, just as an introduction. But so I really heard about GPCR probably within like Michel's group in 2002 during my internship, mm-hmm. And so my project actually was, I was under the supervision of Céline Galès, who's a French researcher. I think in Toulouse, she's still in Toulouse. And,
yes, I think so.
It was funny because our project was to basically design and breath-based biosensor to monitor, the engagement of G proteins to GPCR. And nobody had done that before. I think there were the FRET. Martin Losey has done the FRET biosensor probably a few months before, and he got but it was and so we know it kind of potentially worked. And then the breath nobody ever. There were two other papers of breath mm-hmm. assay at that time, and one was I think one other paper was in bacteria. It was like a study on the clock protein, so they were able to measure like protein association. But it was really at the beginning. I think there's more than 20,000 paper on breath. So
yeah, by now. But wasn't
massive? But
wasn't Stéphane Anger's paper out then? The beta-adrenergic.
That's right. Yeah, there were Stéphane Anger is a professor at the University of Toronto. Actually, he's now the head of one of the institute. I can't remember.
Donnelly, I think.
Donnelly and so in 2002, that you're right. In 2001, Stéphane published the beta-2 adrenergic receptor dimerization. Actually,
yes,
that was the first breath paper, the second breath paper, but the first kind of breath on GPCR paper, and there were other paper after that before Céline and I before the paper went out. But so we test actually the first breath biosensor, and there were Billy Breton, I think, was involved at that time. And I was an undergrad. I didn't know really what I was doing, but Céline gave me the construct. I transfected using like calcium phosphate.
Oh my God!
approach. So I got to bubble these form a precipitate, not too big, not too small, and the right pH. And it never worked really well during the summer, but then it banned because of the temperature. And but it was a great deal. And then we actually were able to pick up like the first engagement of G protein to beta-2 adrenergic receptors using breath, and it was the beta subunit through beta-2 adrenergic receptor beta 1 that works first actually, and so I did the experiments. Céline was doing the alpha, so I did the beta, and that worked actually. And so I present like my work at the lab meeting at the end of my internship, and Michel, you look at the data and say, you bring tears to my eyes. It's just like, And you don't realize at that time, like the value of these, but looking back, like 22 years after, you just, man, this is crazy. It's one, people, the pharmas, they use it now, and there are a lot, and all the credits goes to, I think, Céline Gallès and Michel, really, Céline Gallès was the postdoc. She was the one that was really knowing what
she was doing, And I remember
she was so nice to, she was so nice with me to, let me do these huge experiments. And she was doing it as well, but she was working more on alpha, and then we understood after that you need like all the subunits to have a great signal, but it happens that the beta engagement was one of the first good assay, and for the alpha, they have modification of the assay, and then it works super well after.
Yeah.
And but I remember we went out at the end, and then we went to a restaurant, and there were like I can't remember where, but it was in the Plateau Montréal, Montreal.
Yeah.
And I think like if she paid me like it's a meal. If you can eat the entire meal,
yes,
you don't pay.
It's like a whole chicken or something.
A money price, or
I know the place.
It was a huge burger, but I came very close. I was like, I was like probably in my 20 years old, like at that time.
Wow.
So I could eat whatever.
I just didn't. I know the place.
For these challenges, but I can't. These people, they were so generous. We grow up. We don't know our luck. One of my goals, if I can, do great science and enough, and have the opportunity to we were kids, and give the opportunity to one of the kids and to be very successful. I mean, I cannot thank enough, Céline, Billy Breton, and Michel, these people that were so generous.
Absolutely.
I was nobody, and I'm still,
I feel you. I'm actually at the same time trying to.
I was a kid student, and it's so, science. There's these mentorship things. It's beautiful. You cannot do science without a mentor that protect you.
Yes.
Help you. It's so critical. You cannot do it alone. You cannot do it without a team. You cannot do it if you don't have somebody at the beginning that give you these break that you need to publish at the beginning. And
true.
And then when you have more experience, then you figure it out. But at the beginning, there's no way you can do it alone unless you're really somebody special. But I think that science is made of a lot of incremental finding, and you need to be clever enough, and you need to be well directed through this, when at a young age you have a lot of ideas, you don't know which one to pick.
Yeah, exactly.
So that's the beauty. That's the beauty of being young.
Yeah.
And then you get older, and then you really know which one to pick. And then you get really old, and then you already know what to fill the idea. But then you really know how to which one would be the great one, and you start doing really massive, amazing science when you're getting older, and you have more money to do it.
It comes with experience. You made a couple of great points we're gonna get back to, but I'm on Google Maps, and the restaurant, I cannot remember the name of the restaurant, but there was a Dairy Queen across the street, and it was like this very like Mexican
it was a huge burger, but you can't imagine. It was a burger as large as a plate,
because you had a whole chicken in the burger. It was a Park Avenue.
It was a multi-layer.
Yes.
What was the name of this?
And they had a bar as well on Saint Denis Street.
It's
But while you think about that, I think you made a lot of great points about the fact that with more experience, the older you get, the better sense you get of what will work and what are the questions, and you get the idea about the higher level questions.
Yeah.
And I think you're spot on. It comes.
You also probably have a great intuition of what won't work.
Yes, that's also very important.
It's probably this.
Agreed. Definitely.
And then the things you're not sure, you try it, and most of the time it's going well.
Exactly. But that comes with experience. You have to start at the bottom and do all the training and, run your first gel to run your DNA with not the buffer, but make the gel with water, as we all did, and then wonder why the samples are diffusing, in order to get to a place where you actually have that knowledge to develop that intuition as to what works and what won't work. And spot on.
Yeah, where's the lost time? I mean, we're all like by nature we have a finite time, and that's our problem.
Yes,
we could stay young and try everything.
Yes,
and then it will be we will probably take an eternity to find everything.
Agreed.
That will be a perfect life.
Well,
that could not happen. You have a finite amount of time. You need to be happy with your family. Also, it's important.
Yes.
You have a finite amount of money, and this is good like this because it's forced to focus. And this is the great mystery of my life. Learning when you start to focus, you can be successful, and that's one of the main point of Michel, my mentor. And when I graduated, he told me there's 3 F. It's focus, and focus. I say, okay, nice. That's right. And it was so right.
That's and, gonna be your...
so there's fun, and then you need to work and on a specific aspect.
Yeah. I think that's a difficulty when you're creative, and you when you're young and naive and creative, you think, oh, we're gonna do it all. But actually, no, you don't have enough time, you don't have enough hands, and you don't have enough money. And you have to pick out of all the problems that you want to work on, which one is, finding that balance, which one might be the most successful, which one will make the highest impact, and, and mitigate all those risks at the same time.
And also, we're doing great impacts, but we are always incremental. We can only do so much for discovery. And it takes a lot of effort. Like, innovation, discovery come at a price of a very, very hard work and small increment.
Yeah.
But the problem is that if you stop, it decreases. Knowledge decreases.
Yes.
Not for us, for society. If you stop doing research on cancer, there will be more cancer. And then we will, because people get older, knowledge get lost. And then you certainly can have you be on a way where you wouldn't be able to cure cancer if you don't research cancer. So you need research as a fundamental of society. So at the start of when it all started, you got discovery and research on things, and you can go back to empires like Roman empires, Babylonian empires, where they needed a way, or Egyptian empires, when you needed a way to count for food and store food for a lot of people.
Yeah.
So they invent the way to count. They invent the way to write it down, and it's kind of started this way, and it went back, and then you need to. So if you don't find ways and do research, it will go back. It will get reversed, and that is so important to maintain basic research, actually, and even industrial research. But there is something that is really fundamental and above the idea of being able to found more money than what you invest. There's some things that is at the fundamental of the tissue of the society, of the modern society. If we want to, so the human being has this particularity. We can solve any problem if we want, if we work hard enough. We can solve climate change. We can impact the way we live. We can save our children, our grandchildren. But we need to work and work very hard. And we need to really, really understand that. And I want it to state and be very clear that if you stop doing research, if you don't continue to invest in research, it's gonna regress. It's not gonna stay the same, because knowledge, the shoulder of my predecessor, if it's not written down, it's gonna get lost. If André de Leon didn't publish his finding, we wouldn't understand pharmacology the way we understand it. If Bob Lefkowitz also did not do that, we wouldn't understand. If you would have not been so fascinated by desensitization of adrenaline in a fading heart. It's so important. And I want to make a call. This is like it's above everything, and I think I think everybody, even if you're not a scientist, you can understand that. If you take your car and you drive, you're somebody from the government and you're a minister and you vote law, and if you take your car, you drive to your office. You need to realize the amount of work that is behind this car. Look at the car in the 70s. They were not efficient. They were broken down. They were carburetor, not injector. It costs a lot of gas, and the gas has lead in it. It was toxic. There were a massive amount of research. It's small increment, but then you can take your car and get efficient and go to work, and it seems less. You don't die from certain disease. There's children that doesn't die from certain type of leukemia because of basic research. Every year, there's about 40 new pills that coming out against cancer that are recognized by the FDA, that are approved by the FDA. It's not in the news, but it's going straight in hospitals. And then you don't go and ask the kids, so are you happy to live? They don't realize, the kids doesn't realize that the physician, they just look at this and say, okay, we have a new tool, we're going to try it. But they don't tell the kids. They maybe going to tell the parents, but they don't publicly say it. But it's important to know. And this is all about, because we're still going forward. Science is hard. We had this level of public funding. It's about 11%. So the 1 out of 10 grants written by the most powerful brains in the world or in your country, the only 1 over 10 that got funded. This is totally crazy. But still, the science is going forward, and we must not stop. It's so important, and it's important to teach the kids that science is important, and we need to, I don't want to be alarmist, but, everything is possible. But I will always be a guy that will, say that we must go forward. We must still invest in basic science without the idea of getting our money back, because we're getting back our money. We're surviving. As a human being, as a society, we're curing people. It helps, and we must not regress. And so that was something I wanted to say. It's so important, and it's so important.
I'm all ears. I'm just trying to turn on the lights because the sun went down.
I broke your light.
Yeah, no, you did not. No, I did not turn it on because the sun went down. No, totally agree with you, and I think I think I was listening to a video from Jordan Peterson, and he puts it so eloquently and so nicely that he explains how far we have come over the years and how we should think about all the difficulties that generations before us, who didn't have the medications, who didn't have the vaccines, who didn't have the hygiene, all of these things. So actually, I don't know if it was Jordan. Anyway, I cannot remember who it was, but it was about a book. And then there's a book written where they talk about all these discoveries and the fact that actually, although we all will still have problems in the world, we have come such a long way. Yeah. And there are reasons to be grateful for what we have and to look back at how far we've come. I have to find that book, because the title of that book, I will send it to you, because I thought it was just so eloquently put. And it was science-based in the sense that they did gather the information, and there was verified data in different fields that showed that we're pretty good, actually. It's not that bad.
It's not that bad. And there's a lot of things that went out from endeavor that were not so obvious at the beginning. Putting a man in space.
I know.
You got these the Mercury program. They were launching people like one after the other, and and they were John Glenn or the Alan Shepard, I think, or maybe the Gemini one. I can't remember, but you have this in the science museum, every science museum. One of the things is that when they were launching people on suborbital, so they were not like turning around. Why? Because if they would have, so the first time they basically wanted to really, hey, let's turn around, a few times. Well, that means like getting like more than 12, 24 hours in space.
Yeah. So,
but you're in a small capsule. So basically, as a human being, what do you do to go to the bathroom? So that was the main problem. So there's a guy in Pasadena at that time, and he's still alive. And I met him once, and he was at that time he was a industrial designer, and he designed the diaper for the space program, and then he got rich, and then he's still. I hope he's still alive, but 5 years ago he was alive, and he's a investment angel in Pasadena, and he was one of these angels. There's a lot of famous people, angels in Pasadena, in California. So it's basically a neighborhood of Los Angeles, and so the guy, even the small. So imagine the impact of a diaper. What's going on? With that. What creates? It's one of the great things of the a lot of family and a lot of men also. And good application for elderly also. So it allowed people to live sometimes when they get problems that they can live a normal life. So it was a great invention. There's other stuff, the Apollo computer for the guidance system. This is the first RAM, the famous pile-in, pile-out, of the information. Error code, that allowed you. How can you focus the computing power of a computer to the most important thing? So you got error code, and you got the way to prioritize all these. So all these algorithms on a modern computer is based on how can we put a man on the moon. And that was fantastic. It's probably easier now to put a man on the moon. It's more but now it's getting money to do it.
Exactly. Problem. And now you can be a space tourist too.
It's a financial problem.
I know,
but there's too much people that think, how can we have our money back? But it's not the point.
You have a legacy that comes with it. But if you just think about just the iPhone, or just a smartphone. I mean, it's a camera, it's a recorder. You can make a video. You can calculate stuff. It does all of these things. I mean, even just an Apple Watch.
Yeah. I mean, I remember. Amazing. So the first thing that really struck me was before the iPhone was the iPod.
Yes, and I
so
had
you got
one.
the music stuff, and then they come up with the iPod with the screen.
Yes, I did not have that one.
And I remember I was with Billy Breton in Paris. Okay, we had these who were really active students. So we went to, I think we went to a garden conference in Italy at that time. At El Chocho. And then
wasn't it in 2005? Maybe not, because that's the
probably.
one.
You say no. Approximately, I think it was like 2009 or.
Okay, I wasn't
just after 2008.
Okay.
Nearby this, probably 2009. I can't remember, but I should look at my resume. But
I was only once in at that resort in El Choco, and it was beautiful. And I think it was 2005, and I remember seeing Billy there, but I don't remember seeing you there.
So Billy and I, we went back and we passed through Florence and in
I
Italy,
did that
and then
too.
we went back to Paris because we had a friend, very, very good friend that, still calling a friend. I can't remember his name for on the spot. It's been like too many years of a bad friend. But he was a PhD student at Cochin Institute in France. So he had an apartment at the 16e arrondissement in Paris. So he was not there, but he'd say, "Hey guys, there's no problem coming back from Italy. Just took the keys. It's under the carpet in front of the door, and you'll help yourself." So we got this nice apartment for a few days, like in the 16th neighborhood of Paris. That was fantastic. I was with BD, and the only thing we had, to get ourselves like walking around was an iPod.
Wow.
And Billy was using his iPod and was talking to his it's his wife Madeleine, and at that time, and I remember, so he was using like wireless. So even at that time in Paris, you got so many wireless antenna. So Apple was able to triangulate your position. So there were no like such thing as cell antenna, because this is the iPhone.
Yeah.
And but we were able to triangulate using map our position just with the wireless antenna. So we're walking, and it's the first time I saw this stuff. Like you update your position in real time. Wow. This was a big deal. I remember at that time I say, "Man, I'll be seeing buying share of Apple." That time it was worth probably $10. I don't know. But at that time I was a fresh graduate student. I had no money.
Yeah.
So I remember thinking, this company is gonna rule the world, and it did. And there's other company like such a Google that did the same, and then they actually have a Mac.
Yeah.
Mac. And
you're gonna laugh because you mentioned how like wow factor it was, having the map on the iPod and you could triangulate your position. The other day, my husband airdropped something on the computer. Oh no, I actually airdropped I was looking at a paper on my phone, and I was like, oh, I cannot read a PDF on my phone. Come on. So I was like, oh, let's just airdrop it on the laptop. And it was instantaneous. And believe it or not, I was amazed. I was like, wow, this is so amazing. Instead of having to download it on your phone, which is already a big deal, and then attaching it into an email and then sending it to yourself and then open it. No, you just airdrop it. And this is amazing.
It's amazing. I mean, I have this habit that, prevent me sometimes to use the full power of the technology. For example, I have an Android phone and my computer is a Mac. I don't know. I had the opportunity to buy an iPhone. I did that. I should have. The only thing, the camera at that time was better on the Android. But I wish. I think my next phone will be really an iPhone.
I just switched, and I was an Android person for a very long time, Mac for computer, Android for phone. And last year, we switched, both of us actually. And the question I asked myself is, why didn't we do this sooner? Because it's different. Don't get me wrong. It's different. I loved my Android, but it's just, it knows things and you can spend hours, setting it up, and it just understands you well.
Yeah, it's like a automatic. So when I kind of get it when I talk to for Mike Hansen, the scientist. I think he's working at Schutte right now.
Mm-hmm. Yes.
He's one of the guys that crystallized the S1P1 at that time. Mm-hmm. He was a PhD student in 2012, and he was working for Receptors after. And
yes,
but he's one of the guys that really trained me hard, really at the synchrotron. Like, he showed me everything, and we went a couple of trips. And, it was so kind because he had a big family at that time. Probably his last trip at the synchrotron was with me, and so I asked him, you got a Mac, you got a tablet, and then you use it. At that time, you could use it as a screen. And I say, you prefer a Mac, but you can use Linux or. And then he answered me like, one of the things with Mac is that, there's a lot of things you don't need to think about. And you can focus on your production. That's what you're doing, actually, what you want to do with and actually that's really powerful. That's right. Sometimes with Windows and especially with Linux, you're always stuck somewhere, and even to download like a library to compilate your damn program, you need to download your compiler. That's crazy. So with your Mac, if there's a problem, you got an update from Mac like during the night, and that's
exactly. It just solves itself. It's kind of having a Tesla that updates itself. I was walking by a Tesla the other day, and I guess I was too close. And then on the big monitor, there was this eye that popped in and said, "You're being recorded."
Yeah, exactly.
Which I thought was wow. So the Tesla just spotted me. Or the other day, I was walking by another Tesla, and it said, there was a message on the screen because there was a pet in the car. And it said, "My owner will be back shortly. The AC is on," which I thought was amazing. And I know we got completely derouted in the conversation from GPCRs and stuff, but the point is investing in basic research, investing in research, not necessarily, only in the field, but investing and putting the time to develop new tools that can make our lives better, that can make our lives longer and healthier, is worth the time and effort and money that we put in it.
Yeah, I totally agree. Like, one of the examples is that the anti-hypertension pill. Like, so these, like, there were massive amount of investment, billions and billions everywhere in the Western countries.
Yes,
for like almost like probably 30 to 35 years.
Mm-hmm.
And we end up in, I think, like, really great, and the pill that we have right now, they work for a lot of people, and it sometimes not, and we still need to understand it, but these like, they're saving lives of a lot of people. They're prolonging life of people a lot,
Yes.
And
there is more to be done, because now we're at a point where we can actually personalize and make sure that that pill is specific to you, to your genes, to your repertoire. So I think it's just fantastic.
I think now also we need to learn how to eat well.
Well, that's
we need to get out
another
of
topic there. But definitely, but I think yes, agreed. But then again, I think we've come such a long way that there is much more to do. And we can be more surgical, more precise, and hopefully, prevent more diseases before they even appear.
Yeah, there's still too much people dying from heart failure.
Yeah.
There's diseases we can't help. pulmonary hypertension,
Yes, exactly.
kind of fibrosis and typical things. You got like a woman that gave birth and then she got diagnosed and started to cough, and next thing she has 5 years to live. And so these type of disease, cardiovascular disease, they're terrible. Cancer is terrible. We're starting to understand how the immune system kind of works towards that, and how it froze sometimes.
Yeah, exactly.
Immunotherapy works for some application when you got active leukocyte that you can grow and then you can work it out. But there's still so much to understand, and we have never been so advanced in having tools to be able to figure it out. And we just need to still push and get the right public funding and the right idea and push on it. I think we have to still continue to push, and we're close in a lot of area, and there's a lot of breakthrough every year. There's a lot of solution, and it seems to be a healthy transfer of knowledge from the public knowledge towards like industry that are able to manage the information and develop the right stuff, because this is another scientific problem. All the development process of a pill, this is complicated. People don't realize like how difficult is it. It's so difficult. You get to, and it's not because they are not trying it. It's they're everything that works. It's a success. It's a money success for a company.
Yeah,
you need to put things that works on the market. The FDA won't approve it, and so but it's so difficult. So
it is. 2 points to add to that. Any disease you can think of, there's always a GPCR involved. Hence, you're never going to run out of projects. And there's going to be projects for your students and many generations. The other point is, and it is difficult to go from an idea to understanding the biology of the target, identifying the target, understanding the biology, and developing an getting to an FDA approved drug. And there's two thoughts that come through my head. Is one, it's difficult for one person to be involved in all of those steps, and you think, well, I'll do my best. Two, it's a huge machinery, and in order to get from point A to point Z, everyone has a role to play in it. The basic scientist, the pharma company, the scientist of the pharma company, the regulatory bodies within the company, the FDA type of regulatory and Santé Canada and all of these. But it's the collection of people and the common effort that gets from that point A to that pill or to that medication or to that antibody, you name it. And I think I'm always amazed by the fact that it's not the sum of all of these, it's the exponential. And what are you still need luck to get.
Serendipity is key, and but you need a process to I will say optimize serendipity.
Yes, yes, exactly. Optimize serendipity.
To get back to the concept of the timeline of a pill, people don't realize that when you take a pill, like, most likely the guys that does, or the girl, the woman, or the people that does the initial discovery, actually, they most likely have been discovered that when they're young, and they're going to be far retired when the actual pill is going to be on the market. It's so tough. You need to develop, make sure that it's not toxic, and make sure that it does. You need to optimize it. There's a lot of things there's a lot of things we know can reduce like a cancer size, but it actually is going to kill somebody.
Exactly.
So you have these shelf compound, everywhere in pharma company that they need to make sure that the one that not gonna be too toxic is going at the end. And this is a very complicated process, and that's making the link. Structural biology is one of the great catalysts to understand how to, design a drug or maybe conserve the properties of your drugs. If you understand how it acts to the target at the atomic level, using high resolution structural biology such as X-ray crystallography, you'll be able to help chemists at every stage, like even like at the early stage, where you basically look at and synthesize everything that could work on your targets, and look at the affinity, and then inform actually predict when you try to get your PK/PD better, or the distribution you want, or the absorption you want. Then inform the chemist that you may want to do these modifications, but cannot do these other because it won't fit in the pocket, or it won't address the right efficacy. And if you understand how the pocket works in initiating the efficacy on the receptor, for example, then you have the perfect keys. And one of the great examples is like Receptos with S1, the S1P1, where it took 7 years only. So it shortened the time a lot for the early stage development until the end of phase 2, actually. Yeah. So and this was like a compound for so it's been bought by Celgene, and then it was in collaboration with another company at the end. I think it's BMS. I can't remember.
Wasn't the FTY 720 molecule?
Well, yeah. Like that. Yeah, I can't remember.
Yeah, I can't remember either. I think it's late. I think that's the
it's
cue.
Multiple sclerosis application. So
yes, I think that was it. That must have.
But so structural biology is so important, and I think it get really recognized in the company also. The problem is we need to train more people for that, and it's a lot of running a structural biology lab. It costs money, and it I've been lucky like so far, and but it's been a challenge, I will say, in terms of infrastructure. So
especially if you're in an institution where you're the first one.
Yeah, exactly.
And I think that's definitely challenging.
Yeah, well, I think they're doing what they could also, like, to help, and I'm not alone, but they're doing their best, but everything stems from and you need to have like solid public funding to being able to go for it. And I think I would love to see enthusiasm in terms of public innovation, and a deep understanding of the necessity of and the necessity of basic science, and the high funding in basic science, and I cannot stretch it so much, and after that you train people, and these people will start companies. They will they will get. It's not everybody who want to do basic science, but you can train them to be very, very good scientists, and then they will challenge pipeline in the industry, and they will do fantastic stuff, and you never gonna heard about these people, but these are the core of pharma industry, and they're bright people, and very and they're all been trained in universities, but doing basic science. They're super bright people, and knowledgeable, and so it's important. It's the base of everything, and we must not stop.
You make a phenomenal, great point. And after that, I have two other things to add. Great point as to the fact that studying and working in basic science provides you the tools to contribute to it, to develop an expertise, but it also teaches you something very important, is how to think scientifically. And that knowledge, or that process that you develop, after that comes the intuition, and with that you can basically go and do anything in any context, because you have the scientific thought process with you, and then you have that optimism, but also that skepticism, and that really going into it and going at it logically, scientifically speaking.
Yeah, and then it's kind of
Yeah, please go ahead.
Sorry.
No, it had
and
nothing.
also the intuition also.
Yes,
even on
exactly.
management, it's the same, involving intuition and even in management and the interest, the way you interact in a scientific meeting with people, and pick up their mind, and after you can read in people's emotion, and you can prevent things in management, and you can be a very nice person in every field, actually, if you can.
Exactly.
There's a lot of translational aspect in studying, having a degree in science. And
I think so too. Point number 2, I think the restaurant name was Alsatium.
Oh yeah,
I just remembered it.
What was the name of the burger?
I don't think they exist anymore, but they had a bar as well called the Alsace Bar on Saint Denis. But the restaurant's name was Alsatium. It just came to me. I was listening, but it just came to me. I don't know if they were.
They should have like the.
And you get a T-shirt. You got a
Google.
T-shirt.
Yeah. I think I should have. I came close to finish, but I didn't.
Oh, you didn't. So you didn't get a T-shirt. I think
no. But I have a picture here. I think, but it's from
long time ago. All right.
Well, it's not me, but it's on the internet.
Okay. Yeah, I'll link it into the podcast page. Martin, let's pick up, because I think we have later on. I think we have many more things to talk about, and I wanna respect your time, because I know you have other things to do after this. But it was such a great pleasure to talk to you. Let's do a part 2, because I think we still have more questions. I still want to know what projects you're working on. What's your favorite GPCR, or maybe G protein? Who knows? Sometimes people tell me,
they are great, actually, but they're better individuals. That's
But let's go from there, and let's pick it up. Always a great pleasure. I cannot wait for us to record part 2 and discuss.
Thank you so much for having me. It's an honor for me, and I appreciate so much your work. I mean, this is another thing, like you're communicating science. We cannot make it without having someone or a group of people that can reach. And put us together, and then reach beyond science, actually, and communicate. Because the problem of a scientist, we're bad at going to our neighbor and start to talk about it, and then we're trying, and sometimes our neighbor don't want to talk to us because we're talking too much.
Unless they're a chemist or structural biologist.
So your work is so important, and I have so much respect for that, and it's amazing. It's amazing that I know you also.
Oh, thank you. That's very
I feel so fortunate. So thanks for having me. And,
absolutely.
We'll get.
We'll continue. Yes, but let's not wait another 2 years down the line.
No, that's fine. I mean, I have students that are actually doing the experiments now.
Okay, that's good. Okay. That's good.
I can talk.
All right, Martin, I'm going to stop recording. Don't go anywhere.
Okay.
I want to say bye to you in an informal manner. This I typically don't say of recording, but people, every time I say bye to our guests, we talk afterwards. All right. Thank you, Martin. Thank you, everyone, for listening in.
Thanks.
Thank you for listening to this Dr. GPCR podcast episode. I'd like to thank our guest, as well as our team members, Attila Forrest and Ines Pinero. Become a beta tester today and sign up for the new and improved Dr. GPCR Ecosystem 2.0 at ecosystem.drgpcr.com. Please subscribe to the Dr. GPCR newsletter, find us on YouTube, and if you like our podcast, leave us a 5-star review on Apple Podcast. You can also leave us a testimonial at drgpcr.com/testimonials. Another great way to support us is to share your favorite Dr. GPCR program with your network and colleagues. As always, if you have any questions or suggestions, email us at hello@drgpcr.com. Until next time, stay safe.